Okay, this will be my third attempt at making this video. First time I forgot how to solve it and I had to go check my notes again, and the second time I hit a button on my iPhone that shut the video off halfway. So here we go. Third time's the charm. This problem is the same as that problem. Only, instead of asking you to find the amount of work it takes to move the spring from one point to another, it gives you that. It says it takes this much amount of work to move it from here to here, and this amount of work to move it from there to there. And then it asks you to find the natural length of the spring here. So there's the answer. I'm going to show you how to get it. So it's basically the same question as number one, like I said. So we're going to use the same setup. This is how we find K eventually, but well, that's how we get this integral. This integral is really all we need. So this is where I started it the last time I tried to shoot this video, and then this is about where I cut it off. So it gives you the amount of work it takes here, 6 joules, and remember this equals joules because your answer was in joules from number 1. So it gives you the joules here, and then you set up your integral. You got to reverse engineer it a little bit. That's why we're engineers. Go college engineering. In the problem, your bounds go from 10 to 12, I believe. Yes, 10 to 12 centimeters. So you're going to set it up so you don't know where your natural length is, because in problem number 1 we had the natural length and we labeled it 0 because that's where the spring just is naturally, and then this is how far it extended out from that natural point. It extended another 5 centimeters, or 0.05 meters. So this 0.1 minus, I'm going to use Z. Z is your natural spring length. So here, this basically says from 0.1 meters outside the natural spring length to 0.12 meters outside the natural spring length. This factors in the spring length, the natural spring length, so we can solve for it in a second. And then we're going to use the standard setup. We're going to use kx dx. Okay, so now that we got that, sorry this is so drawn out, but it's a lot to, this problem's tricky. Okay. Yeah. Alright, so then after you've plugged all that crap in, you get 6 equals, give me a sec, K, and all of this is going to be over 2, because, yeah, K, I'm going to go top bound minus the bottom bound, so 12 minus Z squared. I'm looking through my iPhone to write all this. Keep in mind it's very difficult. There's a bit early bad glare from the lamp. Minus K, and then your other bounds 0.1 minus Z. The first time I did this, I had my bounds backwards. I said Z minus 0.1 to Z minus 0.12. I got some crazy freaking answer, and that's when I just gave up and went to the internet. This is why the internet rocks, because you got people like me who have already made the mistake, right? Yeah, okay, so then you get this stuff here. Oh, yeah. And then what you're gonna do is you're going to basically you can factor out all this stuff here. So you've got 12K equals 0.12 minus z squared minus 0.1 minus z squared. And then, unfortunately, yes, you do have to do these out, expand them. What you get in the end, because this video is already 5.5 minutes long, is k equals 8 centimeters. So what you're going to wind up with really in the end is you're going to get 0.8. Don't worry, remember this is in meters. So don't put 0.8 meters into WebAssign because it's in units of centimeters here. Cool. We did it. Okay, peace. I'll now make one for problem number 3.